Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at self-adjoint and skew-adjoint linear operators. So in this topic, we will define self-adjoint and skew-adjoint linear operators. We will see that symmetric real matrices and conjugate symmetric complex matrices are self-adjoint. We will see that skew-symmetric real matrices and conjugate skew-symmetric complex matrices are skew-adjoint. We will learn that every linear operator is the sum of a self-adjoint and a skew-adjoint linear operator. Let's start with two definitions. A linear operator, A mapping a vector space to itself, is said to be self-adjoint if moving the operator to the other side of the inner product results in the same calculation for all vectors u and v. A linear operator A is said to be skew-adjoint if moving the linear operator to the other side of the inner product results in the negation of the value of the inner product, again, for all vectors u and v. Now, self-adjoint operators are critical in your course in quantum mechanics. For given a wave function that describes the momentum and position of a particle, operators that extract information about the position, the momentum, the energy of those particles must be self-adjoint. Now, the adjoint of a real matrix is the transpose of that matrix. So the ijth entry of the transpose is the jith entry of the actual matrix itself. So for these two to be equal, we require that the ijth entry of the matrix equals the jith entry of the matrix. In other words, a real square matrix is self-adjoint if the entry above the diagonal equals the entry in its reflection through the diagonal. Because of this reflective property, we call such matrices symmetric. This matrix here is symmetric, and therefore it is self-adjoint. Again, if we take a look at the entries reflected through the diagonal, we notice that they are the same. For example, the entry at 1, 3 is 0.7, and the entry at 3, 1 is also 0.7. Now, let's check if this property is true. Here we have a matrix that is symmetric. Here are two vectors, u and v. If we calculate the inner product of a times u, we get the vector 3, 5, 8, negative 6, and if we take the inner product of this result with the vector v, we get negative 8. Similarly, if we multiply a by v, we get the vector 5, 1, 0, 3, and if we take the inner product of u and that result, we also get negative 8. Notice that if we change even one value in the matrix, it no longer holds in general that we can move the matrix over. So here, the matrix A is not equal to its transpose. If we calculate A times U for this non-symmetric matrix, we get the vector 3, 5, 8, negative 5, and if we take the inner product of that result with the vector V, we get negative 7. However, if we multiply V by this matrix A, we get the vector 5, 1, 0, 2, and if we take the inner product of U and that result, we get a different value, negative 6. Note, however, that if we move the operator to the other side, taking its transpose, we do get the same result. So again, if we take the transpose of A and multiply that by V, we get the vector 5, 1, 1, 3. which is different from A times V. And now the inner product of U and A transpose times V is also equal to -7. Now, the adjoint of a complex matrix is the conjugate transpose of the matrix. So given a square matrix A that is complex, then the entries of the conjugate transpose are such that the ijth entry of the conjugate transpose are equal to the conjugate of the jith entry of the matrix. For these two to be equal, we require that the ijth entry is equal to the conjugate of the jith entry. In other words, a complex square matrix is self-adjoint if the entries on or above the diagonal equal the conjugate of the entries in its reflection through the diagonal. Because of this property, we call such matrices conjugate symmetric. Theorem: the diagonal entries of a conjugate symmetric matrix are real. Proof: well, if Aij is equal to the conjugate of Aj for all I and j, then if I equals j, we require that the diagonal entry is equal to its conjugate. Well, this is only true if the diagonal entry is real. Consequently, all the diagonal entries must be real. So let's see if this result is actually correct. As an example, here we have a matrix that equals its conjugate transpose. So here, the diagonal entries of A are real. There's real entries off the diagonal as well, but that doesn't matter. But for each entry off the diagonal, that entry is equal to the conjugate of the entry that is reflected through the diagonal. So for example, the entry 1, 2 is 1 minus j, and that is equal to the conjugate of the entry 2, 1, which is 1 plus j. Now, here we have two vectors u and v. If we multiply u by a, we get the vector 3, 5 minus j, -1 minus 2j. And if we take the inner product of that and v, we get a result of 9 plus 3j. Now, it's important to remember that when you're taking the inner product of complex vectors, you must first conjugate the entry in the first argument of the inner product. So, for example, here you would multiply 3 times 2 plus j, 5 plus j times 1, and -1 plus 2j times j, and add those together to get 9 plus 3j. Also note that if we calculate a times v, we get the vector -2, 3 plus 4j, and 6 minus 2j. And if we take the inner product of u and this result, we also get 9 plus 3j. If the matrix is symmetric but not conjugate symmetric, this property no longer holds. So here we see the matrix A. It's actually a symmetric matrix and not a conjugate symmetric matrix. So if now we calculate A times U, we get the vector 3, 5 minus 3j, -1. And if we take the inner product of that result and V, we get 11 plus 5j. However, if we multiply the matrix A by V, we get -2, 5, 4 plus 2j. And if we take the inner product of U and this result, we get 11 plus 9j. Note, however, if we use the conjugate transpose when moving A from one side of the inner product to the other, we do get the same result as expected. For the adjoint of a complex matrix is its conjugate transpose. So if we take the conjugate transpose of A and multiply it by V, we now get the vector 2j, 3 plus 4j, 4 minus 2j, and taking the inner product of u and that result also gives us 11 plus 5j. Now, for real skew-adjoint operators, again, recall that the adjoint of a real matrix is the transpose of that matrix. And given a matrix A, then the entries of the ijth entry of the transpose is the jith entry of the original matrix A. For A transpose to be equal to the negation of A, we require that Aij is equal to the negation of Aji. In other words, a real square matrix is skew-adjoint if the entry on or above the diagonal equals the negation of the entry in its reflection through the diagonal. Because of this property, we call such matrices skew-symmetric. Theorem: the diagonal entries of a skew-symmetric matrix are 0. Proof: well, if Aij is equal to the negation of Ji, then if I equals j, that is, we're on the diagonal, this requires that Aii is equal to the negation of Aii. But this is only true if the diagonal entry is 0. Consequently, all of the diagonal entries must be 0. The following matrix here is skew-symmetric and is therefore skew-adjoint. Notice that all the entries on the diagonal are 0, and, for example, the entry at 2, 4 is 0.9, which is the negation of the entry at 4, 2, which is negative 0.9. Let's check if this result is actually correct. Here we see a skew-symmetric matrix. That is, all the entries on the diagonal are 0, and any entry off the diagonal is equal to the negation of the entry in the reflected position through the diagonal. So, for example, entry 2, 4 is 1, while entry 4, 2 is negative 1. So if we take if we multiply a by u, we get 6, 1, negative 1, negative 2, and taking the inner product of this and v gives the result of 11. If we multiply v by a, we get the vector negative 1, negative 3, negative 1, 1, and taking the inner product of u and this result gives us the value of negative 11, which is what we were expecting. Note if we change even one value in the matrix A so that it is no longer skew-symmetric, then if we calculate A times U, in this case getting 6, 1, 1, negative 2, and take the inner product of that and V, we get 9. This is not equal to the negation of A times V, which is negative 1, negative 3, negative 5, 1, and taking the inner product of u and that result, negating it, gives us a value of 15, which is not equal to 9. Now let's look at complex skew-adjoint operators. The adjoint of a complex matrix is the conjugate transpose of that matrix. That is, the ijth entry of the conjugate transpose is the conjugate of the jith entry of the matrix. Now, for A to be the negation of the conjugate transpose of the matrix, we require that the ijth entry of the matrix is equal to the negation of the conjugate of the jith entry. So in other words, a complex square matrix is skew-adjoint if the entry on or above the diagonal equals the negation of the conjugate of the entry in its reflection through the diagonal. Because of this property, we call such matrices conjugate skew-symmetric. Theorem: the diagonal entries of a conjugate skew-symmetric matrix are imaginary. Proof. Well, if the ijth entry of the matrix is equal to the negation of the conjugate of the jith entry, then if I equals j, it follows that the entry on the diagonal must be equal to its negation conjugated. Well, the only times that a complex number equals the negation of its conjugate is when it is imaginary, and therefore all entries on the diagonal must be imaginary. Let's check if that's true. Here we see a matrix that is conjugate skew symmetric. All the entries on the diagonal are imaginary, and the entry at, say, entry 1, 2 is equal to the negation of the conjugate at the entry 2, 1. So, given the vectors u and v, if we calculate the inner product, or if we calculate a times u, we get the vector 4, 2, negative 3 minus 2j. And if we take the inner product of that and v, we get the value 8 plus j. If we multiply a times v, we get the vector j, negative 1 minus j, minus 4. And if we take the inner product of u and that result, we get negative 8 minus j, which is the negation of the previous result. Note that this inequality is false if the matrix is simply skew-symmetric and not conjugate skew-symmetric. So for example, here we see a matrix A that is skew-symmetric, but it is not conjugate skew-symmetric. Now if we calculate A times U, we get the vector 4, 1 plus j, negative 3, and if we take the inner product of that and v, we get 9. However, if we multiply v by this matrix A, we get the vector j, negative 3 plus 2j, negative 4 minus 4j, and the inner product of u and this result is negative 13 minus 8j. Now a comment on terminology. Just like the conjugate transpose is sometimes called the Hermitian transpose, a conjugate symmetric matrix is sometimes simply said to be a Hermitian matrix, and a conjugate skew-symmetric matrix is sometimes said to be a skew-Hermitian matrix. Now, from calculus, recall that a function is said to be even if f of negative t is equal to f of t for all t. Now, to reiterate, the term even comes from the fact that all even powers of t share this property. So for example, here I have a polynomial that has terms with only even powers of t. If I now substitute into this polynomial negative t, well, I get the original polynomial back. So this polynomial is symmetric through the line t is equal to 0. Recall that a function is said to be odd if f of negative t is equal to negative f of t for all t. And again, the term odd comes from the fact that all odd powers of t share this property. For example, again, consider the polynomial 3t to the 7 plus 2t cubed plus 5t. If I substitute into this polynomial negative t and expand, I get that this is the negation of the original polynomial. Now, you may recall that the cosine function is even and the sine function is odd. So from calculus, here's a theorem. Every function is the sum of an even and an odd function. Proof. This is actually a constructive proof. I will define f even, or the even component of f, to be the function defined as f of t plus f of negative t all over 2. I will define the odd component of f to be f of t minus f of negative t over 2. The first thing we note is that f of t is indeed equal to the sum of these two functions we have just defined. However, on top of that, if I substitute in negative t into the even function, well, we get what we see here, and negative f of t is just f of t, and because addition commutes, well, that's just equal to the even component of f evaluated at t. So yes, the even component is indeed even. Similarly, if I evaluate the odd component of f at negative t, again, we substitute that in, and we note that that simplifies to that expression here, and I can factor out a -1, and so we get that the odd component evaluated at negative t is the negation of the odd component of t. So here we see that f is the sum of an even function and an odd function, and consequently we are finished. From calculus, you may note that the Taylor series of an even function is comprised entirely of even powers of t, and an odd function is comprised entirely of odd powers of t. Here's the Taylor series for e to the t, and we note that e to the t is neither even nor odd. However, using the construction from the previous theorem, we can create the even component, shown here in green, and the odd component, shown in blue, and we see that yes, indeed, the even component is comprised entirely of even powers of t, and the odd component only includes those terms from the Taylor series that are odd. So now we have the following theorem. Every linear operator is the sum of a self-adjoint and a skew-adjoint operator. Proof. Well, as before, this will be constructive. I will define the self-adjoint component of A to be A plus the adjoint of A all over 2. The skew-adjoint component of A will be defined as A minus the adjoint of A all over 2. Note that if I take the conjugate of the self-adjoint component of A, well, that's just the adjoint of this sum of two operators, all over 2. But the adjoint of a sum is the sum of an adjoint, and the 2 can come out. So that's equal to this expression here. The adjoint of the adjoint is equal to the matrix or the operator itself. And oh, wait a second. Operator addition is commutative, and so this is equal to the self-adjoint component of A. So yes, as defined above, that linear operator is indeed self-adjoint. If I take the adjoint of the skew-adjoint component, again, this is the adjoint of a sum of adjoints. Basically, it's the sum of a linear combination of operators. So bringing that in, we get that expression here. Once again, the adjoint of the adjoint is the linear operator itself. And well, now I can factor out a -1, and we see that this is the negation of the skew-adjoint component of A. So yes, the skew component of A, as defined above, is indeed skew-adjoint. Thus, the statement is true. To show this theorem in action, consider the following real matrix. Now, for a real matrix, the adjoint of the matrix is the transpose. Consequently, to get the self-adjoint or symmetric component of the matrix, then we just add A plus A transpose all over 2. So with that calculation, we get this matrix here, which we see is indeed symmetric. The skew-adjoint component is found by calculating A minus A transpose all over 2. And once again, if we calculate this, we see the skew-symmetric matrix we see here. All the entries on the diagonal are 0, and any off-diagonal entry is the negative of the corresponding entry reflected through the diagonal. Following this topic, you now know what a self-adjoint and a skew-adjoint linear operator is. You understand that a real symmetric matrix is self-adjoint and a real skew-symmetric matrix is skew-adjoint. You understand that a complex conjugate symmetric matrix is self-adjoint and a conjugate skew-symmetric matrix is skew-adjoint. You know that every linear operator is the sum of a self-adjoint and a skew-adjoint linear operator. You also know that the defining feature of a self-adjoint operator is that given an inner product, you can apply the linear operator either to the first term or the second term, and you get exactly the same result. And the defining feature of a skew-adjoint operator is that if you move the linear operator to the other side of the inner product, you get the negative of the previous result. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!